Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 16. Student, as in lecture number 14 and 15, basically we start the analysis and design of shear in a flat slab system or flat slab system from lecture number 11, and today inshallah we will cover the whole shear analysis in a flat slab system by covering two examples, right? So basically what we have covered, right, in lecture number 14 and lecture number 15, sorry. So basically we see in lecture number 13 we covered transfer of moments to columns, and we covered these examples, right? We do one example over the transfer of the moment in longitudinal direction, or you can say for these two frames, and similarly for these two frames. And today we will cover one other example, which is basically the rest of the part of this example. So you must watch this lecture, which is, I think so, lecture number 13, right? I have covered this example, so you must have an idea about this example. If you don't know about this example, so you can't understand the present example which I will cover, which will be this one, right? So you must watch that lecture number 13. Then we start basically in lecture number 14 and 15 we understand the different notations which will be used in today's lecture as well, and we see the shear and flexure interaction, right? And we understand thoroughly that how to calculate the shear, right? The shear when we have transfer of moment, when we have a shear flexure interaction, right? We code different ACI criterias, okay, regarding such situation when we have unbalanced movement, and we understand what is transfer width thoroughly. You must be know about the transfer width, because in today's examples we will use this transfer width. And similarly we understand what is the different properties of shear parameter, right? And we also see when we have to use negative sign, when you have to use positive sign, and we also see how to calculate the polar moment of inertia for an interior column, for an exterior column, and this is for interior column. You see here the formula and how to calculate CAB and CCD in this case. Similarly in the case of an H column, how to calculate your CAB and JC. We already discussed this in lecture number 15. And similarly in the case of the corner column, how to calculate your CAB and JC, right? So if you don't watch that lecture, which is lecture number 15, sorry, so you will be unable to understand the today lecture, right? So in lecture number 15 we also covered this topic, what are the different load patterns for interior column, edge column, and corner column, which will give you the maximum shear and maximum unbalanced moment, right? And similarly we also discuss this, that how to transfer the face movement and face shear to the shear centroid and to the centroid of the column in the case of exterior column, interior column, and corner column. And we also discuss this alternate analysis method, because we already know that we have three methods to analyze the shear flexure interaction. We have ACI commentary method, we have beam method, and we have alternate method, right? And this was basically the end of lecture number 13 to lecture number 14, right? So in today's lecture we will cover the the two examples which the today example is example number 16.7.1 from lecture number 13, and I already discussed this right here, that this is the example, right? This one is the example which I have to cover in my today lecture, right? So here we have Live load is already given in that example. The thickness of the slab is also given, that is 5.5 inch. The average is also given, that is 5.5 minus cover minus, they are using number 4 bar, so that why the net or the average depth of the slab is 4.25 inch, right? The unbalanced moment, we already determined that unbalanced moment in that example, right? And so you must watch lecture number 13, right? So here you see 15.1 is the for the exterior column, right? Here we have to basically use the shear, flexure and direction for exterior column and for interior column. So this 17.5 is basically, you see here, that is the unbalanced movement, and it is, you see here, we will cover this in lecture number 13. Now what we have to do, we have to find out the tributary area for the H column. So how to find the tributary area, I also discuss it in lecture number 13. So find out the tributary area for that H column. If you see here, this is my diagram right here, and for the H column, you see this side, the column strip width are the half of this panel and half of this panel. This is 12 feet, and in this direction it is 15 feet. So 15 divided by 2 give me 7.5 and 12. So this is the tributary area, you can say this area, right? This is the tributary area for the H column, and we find this 90 feet square, and the QU or the WU is 0.198 KSF from lecture number 13. We already discussed it. So my VU is what QU times the tributary area, that is 17.8 kips. My VC will be this one. Okay, you have to use those 3 equations. Okay, and by using those 3 equations, this equation basically govern, right? So what are those 3 equations? You must check those equations as well, because these 2 equations, right? So they are not governing, so that's why, because you see here 5.3 and 5.0, so that's why I'm skipping these 2 and I will use this one, right? So my VC is 45.7 kip, right? And now you have to understand now these diagrams, right? This is my column, this side of the column is 12 inch and this side of the column is 10 inch, right? And this dash line is my, remember, this is my transfer width. I thoroughly explained what is transfer width in lecture number 14 and 15. So you must go there and watch what is transfer width. Now my transfer width, right, it is equals to this face of the column, which is 10 inch plus 3 inch, right? 1.5 to this side and 1.5 to this side. This is according to SA code. So my transfer width is 26.5 inch, and now you have to understand this diagram, right? This is the edge of the column, right? This one is the edge of the column, edge of the slab, sorry. Now you see this side is, this side is my, this is one side of the shear parameter, and this is the face, or this is the front face of the shear parameter, right? And these are the sides, and this is the back side. Now you see here, this is my A, right? This is my A, and this is my B, right? And this is my C, and this is my D, right? So here you see this is my 10 inch and this is my 12 inch, and the dot line which you see here, this is the centroid of the column, right? And the line which is the point which is basically the by intersecting of axis WW and Z axis, this point is basically known as the centroid of the shear parameter, right? This is the centroid of the shear parameter, right? And you see here that, remember, here you see the moment, basically here we are assuming the moment about the Z axis, right? This is important. Due to this assumption, or we consider the moment in this direction, so that why this AB is my front, this DC is my back, right? Now you see that what is my B1 and what is my B2. which is very important, and I already thoroughly explained this in for edge column, for corner column, for interior column in lecture number 14. So please watch lecture number 14 to understand what is B1 and what is B2. This is my B1, right, which is the side which is perpendicular to the movement axis, and remember this side is this AB side is my B2, which is the side which is parallel to the movement axis, right? And how to determine it? So you see my B2 is 14.25 and my B1 is 12 plus the average divided by 2, which is 14.12, right? Now this is the plan view of the edge column and this is the sectional view. So you see this line is basically, here you see this line is my the column face, right? This is my column, right? And this line you see here, which I extend down here, this is the centroidal axis of the column, right? This is the centroid of the column, and here you see this is the face of the centroid of the shear parameter, sorry, and this dashed line is basically now is my face of the shear parameter, and this is the slab, right? This is the slab which is continued in this direction, right? This is the top surface and this is the bottom, and this is my column, right? So the axis, the z axis you see here, which is extended in downward direction, and it basically coincides the WW axis at this point. So this point is basically my centroid of the shear parameter. And remember, we are assuming, as I already explained this in lecture number 15, that VU and MUV, remember MUV is assumed to act at this centroid, which is the centroid of the shear parameter, right? Not at the face of the column, but at this shear centroid, right? And you see my B1 is this one and B2 is this one, right? So you must understand this diagram thoroughly, right? Next you see B0, and B0 is this side plus this side plus this side. So you see the B0 is 42.5 inch. Now next, ACA code 13.5.3.3, the simplified procedure may be used if, let's say, your shear strength of your section is more than VU. As we find 5EC, so if you multiply that 5EC with the 0.75 and still it is more than the VU, so you can use the simplified procedure. So what is a simplified procedure? Simplified procedure is this one, that you see once in that, if let's say for example when we multiply 0.75 to 5EC, we got 25.7, which is more than 17.8. so that why we ACA code allows us to use the simplified procedure. Simplified procedure means that, as you already know, that we basically determine the gamma f from equation, that is 1 divided by 1 plus into B1 divided by B2 gamma under root, okay? So we will use the equation for gamma f. So in this case, if this kind of condition prevail, right, so ACA code allow you that increase gamma f to 1 and consider gamma v equals to 0. This means that the whole moment transfer occurred due to flexure, right? And this means that the whole movement from slab to the column is due to flexure, not by eccentric shear, right? So we consider now gamma f equals to 1, and because this condition prevail, and my MUB, right, the total unbalanced movement is transferred by the flexure, and it will be this one, right? This means that MUV equals to 0 and consider shear independently, mean that this term will reaches to 0, right? So now this is your shear stress will only be determined by VU divided by AC, right? So if let's say if this condition not prevail, or you can say this condition is not fulfilled, So then we will ASA code doesn't allow you to use the simplified procedure, right? So we consider the moment transfer by using shear flexure interaction. We don't consider the simplified procedure, right? We assume that, let's say, this condition is not fulfilled, right? So we have to use then this procedure, which I am going to explain, which is known as shear flexure interaction procedure, right? And this procedure gives us more conservative result as compared to the considering or treating shear and flexure independently, right? In this case, by comparing this procedure with this procedure, which is the simplified procedure, this shear flexure interaction give you more conservative result, right? So what we have to do in this procedure, we have to find out the gamma f. So you already know the gamma f equation from ACI code, and you have to multiply mu. Mu means the unbalanced moment, which is 17.5, right? And b1 is already determined, b2 is already determined. You have to just plug the values. You got the unbalanced moment, which is transferred by the flexure, is this much, 10.5 feet kip, right? And in this case, you see your gamma f is this one, right? This means that 60% of the unbalanced moment is transferred by flexure, while the rest of 14% will be transferred by the eccentric shear, right? You see here gamma v will be 1 minus 0.6, which is 14%, right? Or you can determine your mu v, gamma v times mu, or mu minus mu b, right? So 0.4 times 17.5 or 17.5 minus 10.5, that is the mub. So you got 7 feet moment, right? This is the moment which is transferred to the column by eccentric shear. Now you see we have to design the extra flexure reinforcement for this moment. Okay, so a very important note, flexure reinforcement for moment transfer at the column location, right, by flexure. Now we basically the lectures which I have covered in a direct design method, if you go to my YouTube channel and watch those lectures, which basically I don't discuss this procedure, right? We find out the movement at the face of the exterior column by using this equation, and find out the steel reinforcement, you can say, in the column strip for this moment. But we don't consider the transfer of moment, right, in those examples, right? But here you have to understand this procedure, and you have to add this part to those lectures, right? So here you see that in lecture number 13 we already used this coefficient, right? Basically here let me show you those coefficients, right? These are the coefficients, right? At the m negative at the exterior support, this is 0.26, which gives you this moment. And similarly for positive we have to use this one. Similarly for negative, and for the interior panel we will use this 0.65 and 0.35. You must know about these equations if you watch my those lectures which I have uploaded to my YouTube channel, and those lectures are you can see in this playlist, right? But here I am not discuss the moment transfer, right? So we will discuss it now, right? Now this says that 15.1. now we have word as, let's say we have the column strip. Let's say this is my exterior column, right? And I have my column strip, right? In those column strip I have middle strip, right? Half middle strip and half middle strip. But basically when we are calculating the longitudinal moment at this exterior column, we assume that the moment at this point is 0.26 times of m naught, right? And that moment is now 15.1, right? So, and then we further assume that we have to transfer this moment in lateral direction. You must know this kind of procedure right now at this stage. So in the case of the exterior column, we assume that 0% moment is transferred to columns, middle strip, right? This means that we assume that 100% of the moment is absorbed in the column strip. On the other hand, it is also basically it is not 100%. It is said that 98.8%, round about 99% of this moment is absorbed into the column strip, while the rest of 1%, you can say 1.2%, will go toward the middle strip. But here we will assume that, let's say 100% moment is taken by the column strip and 0% go toward the middle strip, right? Remember, in this case, the width of the column strip is 72 inch. Okay, this is 72 inch. We already discussed it right here. Now, in the column strip, the moment is now this one. Okay, this is the total moment in the column strip, right? Let's say we find the area of steel for this moment is, now as you know the procedure if you watch these lectures, right? So basically we find the steel area, right? Steel area for this moment, and we provide those reinforcement in the column strip, right? So let's say they say that we find that area of steel and we denote that steel area by AS1, right? And we find that, let's say we will assume in number of bars, right, in the 72 inch column strip, right? We will use in number of bars the steel area as 1, and we find, let's say 10 number 4 bar or 5 number 4 bar, and those bars should be adjusted in the 72 inch column strip, right? So but remember, as this steel reinforcement is just only for this moment, right? But on the other hand, we have a moment transfer, right, from the slab to the column, and that moment transfer, as you see here, it is MUB or MUF. So we have to check, we have to provide the steel reinforcement for this moment as well, which is responsible for transferring the moment from slab to the column, right? So what will be the procedure? The procedure is simple. We have, remember, you see, now for moment transfer we need extra bars. I already explained, which will be provided within the column strip, which is 26. This is not column strip, it is the transfer width, right? We need extra reinforcement, and that extra reinforcement will be provided in the column in the transfer width, and we already determined that transfer width is 26.5 inch. So and the moment in this transfer width is MUB, and remember this MUB will exist in this portion, right? And I already explained this is thoroughly in this lecture. If you go and watch lecture number 14, I think so, I thoroughly discussed this diagram, right? This diagram, you see the whole column strip width, but this is the effective column strip width, in which basically the moment is MUF or MUB, and we have to provide extra or additional reinforcement in this width, right? So, but one thing you must remember, that this 0.26 moment is also already present, already acting in this column, effective column strip width, right? So we have to subtract this moment, because we already designed the reinforcement for this moment. So we have to subtract this moment from the MUB, because you see the procedure right now. We have two options. We have two options to go forward. Option 1 is this one, which is a difficult one. Find the moment in the transfer width. How to find the moment in the transfer width? So you see MTW. Now you need to understand this diagram, right? You see this is my column, right? And this is my transfer width. This is the width in which basically the moment is transferred from the slab to the column, right? And 72 inch is the column width, column strip width, right? Now the moment in this transfer width, it is denoted by MTW, right? And you see here how to determine that MTW as MUB plus 15.1, right, which is the moment 0.26 times of M naught. 26.5 divided by 72. This factor should be multiplied, and I already thoroughly explained this factor in my lecture number 14. So this basically this is that fraction of moment which basically acting in this transfer width zone, right? Because 15.1 is the moment which exists or which acting in the whole column strip width, but we have to find that portion of this moment which exists or which acting in the transfer width, and this is the portion of that moment which basically acting in the transfer width. So we have to add this with the unbalanced moment, and you got the total moment, which is 16.1. Now you will design the reinforcement for 16.1, but you have to provide that number of bars or area of steel within this zone, right? And the rest of the zone, which is this one, you have to subtract this 26.72. You got the width of these two zones. Now what will be the moment in these two zones? So the moment will be, remember, this is, you have to subtract, right? 15.1 is the moment which basically exists in this total transfer in the column strip width. You have to subtract this fraction of moment, because you already add this moment with the unbalanced moment, or you can say this is the moment which basically acting in the transfer width. So we have to subtract that moment, right? Because we already designed the steel reinforcement for this moment, so we don't need to consider this one. So that's why we are subtracting this moment from the total moment, and the moment which we got here, 9.54, it will be divided by 2 because we have this zone and this zone, so 4.77. Now this is the moment which basically acting right in this portion, and you have to design the steel area for this moment right now. Okay, so let's say you find 5 number 4 bar, so 5 number 4 bar will be provided right here, and 5 number 4 bar will be provided right here, right? And let's say you find here, let's say you find out 10 number 4 bar, so 10 number 4 bar will be provided here, right? This is a little bit difficult procedure, right? But I explain this to you people that you will understand what is going right here. Okay, the next option is simple. The next option is this one, that design steel for 0.26 M naught, which is AS1 already defined, right? This is the usual procedure that we find out the steel reinforcement for the slab, right, at the first or at the exterior edge of the slab. Now after that you have to find out the steel reinforcement for the moment transfer. So then what you have to do, you need here find extra bars for the extra moment caused by the unbalanced moment. So you just simply subtract this fraction of moment from the MUB, which is 5.5 feet. So you need to find, remember, this is very important to understand. If if let's say if it's comes to 0, if this calculation gives us 0, this means we don't need extra reinforcement, we don't need additional bars for the transfer of moment, and the bars which we already calculated by using this moment is enough, is sufficient, right, for the transfer of moment from the slab to the column, right? But if it doesn't give us 0, and like in this case it gives 5.5, so 5.5 is the extra moment now at this phase, and we have to provide additional steel reinforcement. We need to find out the reinforcement for that 5.5 kif moment, and we have to provide those reinforcement right here. Remember, this reinforcement will be provided in addition to the reinforcement which is basically calculated right here, right? Let's say you find the reinforcement in the column strip. Let's say you find 10 number 4 bar, right? 10 number 4 bar. So you have to adjust these 10 number 4 bars in this zone in column strip. Then after that you have to find the extra reinforcement or additional reinforcement for this moment, and let's say those bars are 5 number 4 bar, right? So those 5 number 4 bars should be adjusted in 26.5 width, right? Not in the total width, but those bars should be adjusted in the within addition of those bars which is already provided. So you have to provide these bars as well as these bars, but these bars should be provided in 26.5 to transfer the moment from the slab to the column. I think so it will be clear right now. We will explain this procedure in the next example, right? Already I explained this. Sometime we need extra bars and sometime do not. We will discuss this in coming example. Now the other calculation, as we see that we just only discuss MUV. Now we need MUV, that the transfer of moment by eccentric shear. So we already you people must know about this kind of designation. What does ZX means, what does WWX means, and what is X bar. I already explained this in lecture number 14 and 15. Here I am assuming the movement direction, this one, right, and this is MUV, right? This is my B1 and this is my B2, right? This is the depth of the shear parameter. VU is this one, we already determined. MU, we already determined this is 7,000 pound-feet. We need CAB, I already discussed it in lecture number 15. This is the formula for CAB. You already know all the values, you just plug the value, you got your CAB. This is this one. CCD will be the, if you subtract this CAB from this B1, you got your CCD, which is 9.42, right? And this formula I already discussed in lecture number 15, so go there and watch that lecture. And all the values are known to us. We have to just plug the value, do the calculation by yourself. You got this 4185 inch ki power 4. Now we have to use the shear and flexure interaction formula, which is this one, and this is the diagram, right? Shear flexure diagram, and you already know this is this kind of representation. This is my CAB and this is my CCD, and this is my MUV CCD divided by JC, and this one MUV CAB divided by JC. So you just need, we already know VU, okay, which is this one. B0 we already determined, D we already know, and MUV you already determined this. You just need to plug the values. You got plus 192 PSI, which is the larger shear, right? This one. This is my, remember, this shear is my VUAB, right? This is VUAB, you see here, this one. And this is my minimum shear. But remember, here I am assuming this is a positive. Although this one is positive, but you see this one will be negative, right? You see here, you just need to use the negative sign, and you have to just change this value, right? CCD, right? The rest of the values are same, and you see minus 91. So that designation you must remember that this is my VUAB, and now it is negative, right? This is my this value. So it may be sometime positive, it may be sometime in the next example you will see this value will be positive, but in this example you see this one, in this example it is negative, right? Now next you need your VC. We already determined it. VC can be found by this equation, or you can found this by VC, as we already determined pi VC. So pi VC can be divided by B naught into D, right? So B naught into D will also give you pi VC, right? So my pi VC is 253 psi. If you multiply this with 0.75, you got 190. So 190 psi, you can say it is close to 192, although in shear, basically by using the shear flexure interaction, 192 is more than 190, but we are close. So that why, as we are close, so on the basis of shear flexure interaction, the shear strength is still adequate, right? This is adequate. The next one is the horizontal shear, and I already explained this in lecture number 15, how to find out VUH, and you see this is the VUH, and we already know this equation for VUH, MUV D by 2 JC, and you just plug the value you got. Your VUH is, remember this one. One thing more, you must remember that the sum of the VUAB and this one, if you sum up, right, this is my VAB and this is my VCD. If you sum up these shear stresses, it must be equals to your downward shear, which is VU, right? The next is my interior column. So in the case of interior column, the tributary area will be 12 by 15, right? And you must know that here, right, this is my interior column. So this panel is 15, this panel is 15, and this side it is 12 feet, right? So that's why 15 into 12 my tributary area. My VU is already determined for the, you have to just multiply this tributary area with the QU, you got, this is your VU. B naught is, you must know how to calculate B naught, which is 61, and BC, which will, remember this 4 into FC prime B naught D is a controlling equation, right? And VC is 65.6 skips. Applying ACI, check, right? Simplified procedure as we did earlier. So here you see for interior column it is 0.4, right? We already discussed this limitation of the ACI code in lecture number 14. So for interior column it is 0.4, for exterior this is 0.75, right? So here you see this time it is less than the VU. So that's why we need to use the shear flexure interaction procedure as we did earlier, right? My MU is 9.5 feet kef. I already determined this in this lecture number 13, and for interior column by using the equation, right, for yes, this one you see here, this is 9.5 by using that equation, 9.5 feet kef, right? And here I need my MUB or MUF. This is the moment which is transferred by flexure. So I need gamma F. I just plug the value of B1. This is B1 and this is B2. We already determined this B1 and B2 right here. Not right here. Remember this 10 plus 4.25 will give you your B1, and this 12 plus 4.25 will give you your B2, right? So here 12 plus 4.25, this is B1, sorry, this is B1 and this is B2, right? Because you know that this is the case of interior column, right? So you see this is my z-axis, right? This is my z-axis and this is my column. So here the movement in this direction, right? So this side of the column is 12 inches and this side is 10 inches. So that's why this is my B1, right? This is my B1 and this is my B2, right? So B1 will be 12 plus this d by 2, this d by 2, which is 4.25, and B2 will be this side, which is 10 plus this d by 2 and this d by 2, right? So the gamma f, now you see here, this is 0.5 and 58% of movement will be transferred by flexure. So what we have, the movement MUF or MUB, this is 5.5 feet cap, and MUB will be the total unbalanced movement minus this movement, this is 4 cap feet. Okay, it can also be determined by just subtracting 1 minus 0.58, right? And the value which you got will be gamma V, right? You just need to multiply this factor with this moment, you got this 4 cap feet, right? Now movement in column strip at the interior face of the yes, right, you have to use the same procedure. 37.8, remember I already discussed it here, and you see here this is 37.8, right? This is M negative, a typical interior support, right? And now I mean in column strip, this 0.75 is the coefficient which basically laterally distribute this moment, right? 0.70 basically it is the 0.70 is the coefficient which basically distribute m0 into longitudinally, but 0.75 distribute this moment into longitudinal direction, right? 0.65, not this one, right? This one 0.6 basically distribute m0 into longitudinal direction, while 0.75 distribute the this movement into column strip and middle strip, right? So that way I'm using 0.75. Please go and watch DDM method, because I already explained that if you don't know DDM method, it is difficult to you to understand this method, right? So this is from lecture number 13, right? MCS. Now MCS basically this is the movement in the column strip, because if you know that in a column strip, let me show right here that in the column strip, in the case of the interior column, you know that we have column strip, right? And we have middle strip, half middle strip this one, and half middle strip this one. So the total moment at this point is 37.8, right? And the 75% of the movement will be acting in the column strip, while the rest of 25% will go to this middle strip and will go to this middle strip, right? So now 28.4 cap feet is now here in the column strip, right? 28.4 will be in the column strip, right? And now you see the transfer width is 26.5, we already determined it. Now the column strip movement in 26.5 inch width is this one, as we did in the H case, in the H column case, right? So we have to multiply this factor with this one. So now 10.45 cap feet is that portion of this moment which basically acting in the 26.5 feet, right? Although the total width of the column strip is 72 inches, as we already discussed it, but this 10.45 is the moment which basically acting in the transfer width, and you need to subtract this moment from 28.4, which will acting in the middle strip, in that portion of the column strip. This is the column strip, right? The rest of the moment will act in this zone, but 10.45 acting in the transfer width. This is very important to understand, right? Now here we see that 10.45 K feet is more than MUV, which is this one. So no need of additional reinforcement, and this is the point which I'm trying here to deliver to you people, that sometime we need additional reinforcement and sometime you don't need. So this is basically that's why I'm stressing on this topic right here, that if let's say we got this 5.5, but in this case you see you will got with a negative sign, right? So negative sign means that you don't need to provide the extra reinforcement. The reinforcement which you provide in the column strip for the moment of 28.4 is enough, is sufficient to transfer the moment from slab to the column, right? So we don't need to provide extra reinforcement. And it will also give an idea that in the case of the interior column, right, in the case of the interior column, the unbalanced moment is insignificant, right? And what we have further need, now we have to deal with MUV, right? That is the shear flexure interaction. So we need to find out AC, as we already did it. We need to find out JC, right? I already explained this procedure, that how to find AC, JC in lecture number 15. I explained this formula in lecture number 15. Due to symmetry of the axis, watch lecture number 15, because it is the interior column, so we have a symmetry case. Now we need CAB and CCD. In the case of interior column, these distances are equal and it is equals to B1 divided by 2, right? And this is 8.12. JC is this one. Now you have to use again those equations, right? In this case we have VUAB is 172 while the VUCD is minus 102. Again it is negative, and you have to find out your pi BC, which is 190 psi, and still 190 is more than 172. So that's why our design in shear reinforcement is okay. We don't need shear reinforcement, right? If this pi BC is less than VU, then we will provide shear reinforcement in this layer. Without shear reinforcement, remember this is most important point, which basically I explained thoroughly in lecture number 12, I think so, that if you are providing shear reinforcement, then you can't use this 4, you will use 2. And why? What is the reason? I explained in lecture number 12, right? Then again you need VUH, so MUV times 12 to convert into inches, D by 2, and divided by JC, you got 9 psi is your horizontal shear. The next example from the McGregor, this is example number 13. This example is very important, and I will explain this example because there are so many other concepts. Although the same calculation will be used, right? The same calculation will be used, but it is a little bit different example with some certain additional information for you people, right? So that's why I'm covering that lecture in that example in next lecture, right? Let me discuss that example. Right, the statement is right here, right? This is the statement. Okay, we have 12 by 16 inch column and 4 inch cantilever slab we have, and we already discussed this example a little bit in lecture number 15, in lecture number 14. Okay, the slab thickness is given, this is the slab thickness, this is D average, and the strength of the concrete is given, the strength of the steel is given, M0 is given, right? VU is already given. The portion of the slab outside the center line of the column produces a factor shear force, right? This is the shear force due to the cantilever portion of the slab, right? And this is the inside and this is the outside, right? And it is important, the loading that causes movement about an axis perpendicular to the edge, right? This sentence is very important, right? This is very important sentence and you have to understand this, right? So we will discuss and we will solve this example in lecture number 17. Thank you for watching. See you in next lecture.